Relevance of problem. This problem connects to our topic because it applies Graham's law to show how molar mass affects fusion speed. Earlier in this project, we saw that lighter gases effuse faster. My new problem expands on the idea by using real numerical data to compare effusion times and calculate the molar mass of an unknown gas, turning the concept into a measurable application. A sample of krypton gas effuses through a small opening in 31.0 seconds under the same conditions, and unknown gas effuses in 12.4 seconds. Benefits of problem. Understanding this problem is useful because it shows how Graham's law can be applied to real measurements instead of just theory. By solving it, a student practices comparing effusion rates, working with ratios, and using algebra to calculate an unknown molar mass. These skills help build confidence with gas law equations and with interpreting numerical data. After completing this problem, someone will be able to tackle other tasks, such as identifying unknown gases, predicting which gas will fuse faster in different situations, or comparing diffusion and effusion rates in more complex gas mixture problems. Development of problem. I created my problem by choosing two gases with different effusion times so that way Graham's law could be applied in a meaningful way. Krypton was selected because its molar mass is known, and I paired it with an unknown gas to make sure the problem required real calculation. The numbers were chosen to keep the math manageable but not too simple. The problem is not too easy because it involves comparing times and solving for an unknown molar mass, but it's not too difficult because the values lead to a clear ratio. While developing it, I avoided copying examples from class, using gases already used by classmates, or choosing unrealistic numbers that would make the problem confusing. Uniqueness of problem. My problem is unique because it uses real effusion times instead of giving molar masses like most textbook examples. Instead of calculating a rate, the problem requires working backwards with Graham's law to find the molar mass of an unknown gas. I also chose times that make the calculation meaningful without being too easy. These details make the problem more realistic and more challenging than common practice problems. Visual for problem. The graph shows that as molar mass increases, gases take longer to effuse, matching Graham's law, which predicts a curved square root type relationship rather than a straight line. Light gases like helium move through quickly, while heavier ones such as krypton and xenon take much longer. The unknown gas sits below the trend, meaning it's effused faster than expected for its mass, which makes it useful for practicing how Graham's law can help identify an unknown substance. Formula for problem. This problem uses Graham's law, which explains that lighter gases effuse faster and heavier gases effuse slower. The time a gas takes to effuse is related to its molar mass, which is measured in grams per mole. We use the time for krypton to effuse, the time for the unknown gas to effuse, and the known molar mass of krypton. Graham's law lets us find the unknown molar mass by multiplying krypton's molar mass by the square of the ratio of the two times. Krypton takes 31.0 seconds to effuse, and the unknown gas takes 12.4 seconds. Their time ratio is 0.400, and squaring that gives 0.1600. When we multiply this by krypton's molar mass of 83.8 grams per mole, we get 13.4 grams per mole for the unknown gas. Solutions for problem part 1. We have a given of krypton effusion time, which is T1 equals 31.0 seconds. Unknown gas effusion time is T2 equals 12.4 seconds. Molar mass of krypton, which is M1 equals 83.8 grams per mole. We have an unknown of M2. Explanation: we are trying to find M2 using Graham's law, which relates effusion times to molar mass. Step 2, formula. Our formula is M2 equals M1 times T1 over T2. M1 is known molar mass of krypton. M2 is the molar mass of unknown gas. T1 is time krypton takes to effuse. T2 is time unknown gas takes to effuse. Solution for problem part 2. Step 3, we have to compute the time ratio. T1 over T2 gives us 12.4 over 31.0, which equals to 0.400. Then we have to square, which we have to square 0.400 by 2, which gives us 0.160. Now we have to multiply by known molar mass, which is M2 equals 83.8 times 0.16, which gives us 12.80. Now we have to add 12.80 plus 0.608, which approximately gives us 13.408. Now we have to round, which means M2 is approximately 13.4 grams per mole. Answer: the unknown gas has a molar mass of approximately 13.4 grams per mole. Verification for problem. The solution to the problem is correct. Using Graham's law, the unknown gas molar mass was calculated by squaring the ratio of effusion times and multiplying by the known molar mass of krypton, giving M2 approximately being 13.4 grams per mole. This answer is reasonable because it is lighter than krypton, consistent with the faster effusion time, and falls within the expected range for light gases. The unit are consistent, and the process is valuable to the project because it demonstrates how effusion measurements can be used to identify unknown gases, supporting the experimental and analytical objectives.
Relevance of the problem. The problem that I have connects to the topic of Graham's law, which states that the rate at which a gas effuses is inversely proportional to the square root of its molar mass. The new problem builds on that foundation but adds actual numerical calculations. The concept gives measurable effusion time, unknown gas identity, requirement to use Graham's law mathematically. Benefit of the problem. The new problem provides several benefits. It improves the ability to connect mathematical relationships with real chemistry behavior. The problem requires using numerical values to determine unknown molar mass. The skills gained are mathematical application of scientific laws, problem solving, and critical thinking skills, connecting data to scientific reasoning and laboratory relevant skills. Development of the problem. The problem was developed choosing original numbers that don't appear in textbook examples. A familiar gas like nitrogen was chosen because it has a known molar mass. A new situation was designed where nitrogen and an unknown gas effuse under the same conditions, but different effusion times were purposely chosen so that Graham's law could be applied mathematically. The problem is not too simple because it requires numerical computation. The problem isn't too difficult because it only uses one formula and the numbers are easy to work. The difficulties of writing a new problem were avoiding problems presented in textbooks, choosing numbers that need to work, avoiding unrealistic scenarios, and keeping the problem tied to the topic. The uniqueness of the problem. Graham's law usually follows predictable patterns such as using the same common gases, ask simple comparison questions, provide molar mass for both gases, and rarely involve unknown gases. The new problem takes the concepts of the law but pushes it into a more exploratory context. Instead of just comparing two gases, the new problem has to determine the molar mass of an unknown gas based on effusion time. The graph, the table and plot show for the visual problem. The table and plot show the relationship between molar mass and effusion time. As the molar mass increases, the time it takes to effuse also increases. The points demonstrate helium, nitrogen, oxygen, carbon dioxide, and unknown gas. The pattern shows an increasing relationship. This matches with effusion times proportional to the square root of molar mass. The graph visually proves what the equation predicts, and the curve helps to demonstrate that gases do not change speed in a straight line. The formula The formula starts with Graham's law, which is R2 divided by R1 equals the square root of M2 divided by M1 divided by M2. A supporting formula would be ideal gas law, which is PV equals nRT, N times R times T. The variables R1 and R2 are fusion rates for gas 1 and gas 2. T1 and T2 are measured at fusion time. Constants are molar mass of the reference gas, temperature, pressure unit, and conversion factors. Units are molar mass, time, rate, pressure, temperature, and amount of gas. Graham's law uses ratios, so units cancel as long as the same unit system is used for each like quantity. The solution for the problem, which is to solve for M2, which is T2 divided by T1 equals the square root of M2 divided by M1. The verification of the problem starts with a recheck of the algebra. You have to check the relation holds. They match exactly, which satisfies Graham's law mathematically. It's reasonable because it has direction checks, magnitude checks, and unit consistency. This is valuable to the overall topic because the plug back check shows the solution satisfies the law. It demonstrates how timing, uncertainty affects molar mass. It has unit discipline. It has real world connections.
Relevance of problem. This problem relates to our topic because it applies Graham's law of diffusion, which shows that lighter gases escape faster than heavier gases. Earlier parts of the project focus on comparing rates and understanding how molar mass affects diffusion. My new problem builds on that by using real numbers and requiring an actual mathematical calculation to find the molar mass of an unknown gas. It takes the same concept we learned before and applies it in a measurable situation. Okay, benefits of problem. Understanding this problem helps reinforce how Graham's law works in real situation by showing how gas, speed, and molar mass are connected. Solving this problem builds skills in using formulas, manipulating ratios, and working with real numerical data, instead of just memorizing the concept. It also strengthens the ability to identify an unknown substance based on measurable information. After solving this problem, the student can move on to more advanced topics such as comparing diffusion rates, predicting gas behavior under changing conditions, or calculating how long it takes different gases to escape from containers. Development of problem. This problem was created from scratch by starting with the main idea of Graham's law and designing a situation that requires using real numbers instead of simple comparison. I chose helium and an unknown gas because that combination makes the math meaningful without being confusing. The problem is not too simple because it requires using an equation, rearranging it, and calculating a molar mass. It is also not too difficult because all of the information is provided and the math follows directly from the formula. One challenge is writing this problem was avoiding gases and scenarios already used by my classmates while still keeping it realistic and connected to the topic. I also avoided making the numbers too easy or too complicated so the problem would be balanced and useful for learning. Okay, this is visual for problem, and that's the graph. This table shows how fast different gases escape compared to how heavy they are. Helium from original. Now I have the formula for the solution for problem. First I set the formula. Solution for problem. First I set the formula 54/22 equals the square root of the molar mass of the unknown gas over 4. Then I simplify 54/22, which is about 2.45. I square 2.45 to remove the square root and get about 6.02. Then I multiply 6.02 by 4. This gives the unknown gas a molar mass about 24 grams per mole. Now I have verification for problem. To check my answer, I redo the steps. Graham's law says the molar mass of the unknown gas equals the molar mass of helium times the rate of the ratio square. First, I divide 54 by 22 and get about 2.45. Then I square 2.45 and get about 6.02. Last, I multiply 6.02 by 4 to get about 24 grams per mole. To check it, I plug the answers back in. The ratio of the rates is about 2.45, and the square root of 24 divided by 4 is also about 2.45. They match, so the answer is correct. The answer makes sense because 24 is heavier than helium but lighter than argon, which fits the idea that the heavier gases move slower. The units are right, and the results matches the pattern we saw in the project.
Part 4.1D, resolution of problems. The example problems connect directly to our project topic because it uses Graham's law of diffusions, which compares how quickly different gases escape through small openings. Earlier parts of our project introduces the idea that lighter gases move faster than heavier ones. This problem takes that information a step further by letting us calculate an unknown gas molar mass using real numbers rather than just describing the concept. 4.2D, benefits of problems. Understanding the numeric Graham's law problem helps someone see how gas behavior can be compared and predicted using real data, not just definitions. Solving this type of problem also builds confidence in applying gas laws to unfamiliar situations, which is important in chemistry, environmental science, and even industrial safety settings. After mentioning this example, a student will be capable of tackling more advanced tasks such as comparing diffusion rates, predicting how gas mixture behaves, or calculating molecular speed under different conditions. 4.3D, development of problem. The numeric Graham's law problem was created by starting with the key idea behind the law. Gases with different molecular masses fused at different speeds. When creating this new problem from scratch, I had to avoid several issues. I made sure that the numbers were not too perfect or unrealistic, and I avoided making it multiple choice since the assignment requires actual. 4.4D, uniqueness of problems. Most Graham's law problems found in textbooks or online usually reuses the same pair of gases, the same rounded numbers, or even identical molar masses. To make the problem unique, I selected realistic but uncommon diffusion rates and eliminated any hints that would make the answer obvious. By designing the situation from the ground up, the problem goes beyond common example by forcing students to apply Graham's law to scenarios that they've never seen before. 5.1D, visual problems. As you can see, I did the diffusion rate versus molar masses, and it shows the Difference between the diffusion rates and the molar mass is grams. 5.2D, formula for problems. The formula I use in my brain, the new problems Graham law of fusions, is R1 over R2 equals M2 over M1. Rearranging formula, solving for unknown molar mass. M2 equals M1 times R1 over R2 greater than 2. 5.3D, solution for problem. A gas infused through a small opening, 12.0 seconds, while a second gas B, takes 20.5 seconds. If the molar mass of gas A is 32 gallons molar, find the molar mass of gas B using Graham's law. Simply, the molar mass of gas B is 93.4 grams per molar. 5.4D, verification of the problem. Plugging my values back in gives a ratio of R1 over R2 equals M2 over M1, which matches the original rate time comparison for the problem. This confirmation that the algebra and square root steps were applied correctly. Common gas molar masses are usually between 2 grams per molar and 100 grams per molar. Verification solution shows that Graham's law can be used to identify unknown gases from simple measurement of diffusion effusion.